In this lecture, let's study attention. Attention is an important technique for improving RNN sequence-to-sequence models. Sequence-to-sequence model is a standard technique for machine translation. I assume you know RNN sequence-to-sequence models. If not, you may as well get yourself familiar with sequence-to-sequence models before taking this lecture. Here, I briefly introduce sequence-to-sequence models to refresh your memory. Sequence-to-sequence model means converting an input sequence to an output sequence. For example, it translates an English sentence to a German sentence. The two sentences can have different lengths. Early sequence-to-sequence models are based on RNNs. It has an encoder RN and a decoder RN. The input of the encoder RN is a sequence of vectors. Each vector X is the embedding of a word in the source language. For example, the sequence of x1 to xm is the representation of an English sentence. We seek to translate the English sentence into a German sentence. After taking a vector x as input, the RN updates its state vector h. Vector h is a summary of all the inputs the encoder RN has seen so far. After taking all the x vectors as inputs, the encoder RN stops running. The encoder RN outputs the final state hm. Hm is the representation of the entire input sequence, x1 to xm. If the input sequence is an English sentence, then hm is a condensed representation of the English sentence. Ideally, hm contains all the information of the English sentence. Now it's time to run the decoder RN. The decoder's initial state, S0, is the final state of the encoder. The information in the sequence x1 to xm is compressed into the state hm. We can use hm to generate a German sentence. The decoder network acts as a text generator. In each step, it generates one German word, and the generated word becomes the next input. In this way, the decoder generates a German sentence. Note that hm is all the information the decoder used for generating the German sentence. The decoder does not directly see the English sentence. The translation is entirely based on hm. The sequence-to-sequence model has a critical and apparent disadvantage. The final state, hm, is incapable of remembering a long sequence. If the English sentence has too many words, then hm cannot remember everything in the sentence. If a word has been forgotten by hm, then the sentence generated by the decoder will miss something. The translation will be wrong. If you actually conduct machine translation using sequence-to-sequence, you will obtain this kind of results. The x-axis is the sequence length, measured by the number of words in the input sequence. The y-axis is the blue score, which measures the quality of machine translation. A high blue score means high-quality translation. Without attention, the sequence-to-sequence model deteriorates as the input sentence gets longer than 20 words. If an input sentence is too long, the RN model often forgets part of the inputs, making the translation incorrect. Using attention, the result is the red curve. The blue score remains the same even if the sentence is very long. We are going to study the main topic of this lecture, that is, attention for RN sequence-to-sequence model. Attention was originally proposed by the ICLR 2015 paper. The shortcomings of the sequence-to-sequence model motivated attention. Attention significantly improves the RN sequence-to-sequence model. Applied to machine translation, attention improves the blue score by a large margin. With attention applied, RNN sequence-to-sequence model does not forget the source input, that is, the English sentence. Each time the decoder is about to update its state, attention tells the decoder where to focus on. That is why the method is called attention. While attention improves accuracy, it suffers from heavy computation. Without attention, the RNN sequence-to-sequence model has a linear time complexity. With attention, the time complexity becomes quadratic. I'm about to elaborate on the technical details of attention. To make my lecture easy to understand, I apply attention to SimpleRNN. SimpleRNN is simpler than LSTM and bidirectional RNNs. Attention is applied when the decoder starts to work. Here, the initial state of the decoder at 0 is equal to the final state of the encoder, HM. The encoder records all the states, H1, H2 to HM. Attention compares the decoder's current state as 0 with each of the H vectors. This equation measures how well as 0 matches Hi. I will discuss the align function later on. Let alpha I be the output of the align function. It is a number between 0 and 1. Alpha I is a weight. A big alpha I means S0 and Hi are closely relevant. We are going to use the weights to perform weighted averaging. The encoder has a total of m state vectors, H1, H2, H3 to Hm. So there will be m weights, alpha 1, alpha 2 to alpha m. Each alpha corresponds to an H vector. The alphas are between 0 and 1, and they add up to 1. Next, I will show you how the weights are computed. There are many ways of computing the alphas. Here is one way of computing alpha I. Hi and S0 are two vectors. We concatenate them. Then apply the concatenated vector to matrix W. The matrix vector product is a vector. We apply a hyperbolic tangent function element-wisely to the resulting vector. The output of the hyperbolic tangent function is a vector of the same shape. Finally, we take the inner product of vector v and the output of the hyperbolic tangent function. The product is a scalar. Denote the scalar by alpha tilde I. Here, v and w are the trainable parameters of the align function. They are randomly initialized and then learned from data. V and W are shared among all the align functions. No matter how many H vectors and S vectors the sequence-to-sequence model has, there is only one V vector and one W matrix. After computing all the alphas, we normalize them so that they add up to 1. We can simply use the softmax function for normalizing the alpha tildes. Denote the outputs by alpha 1 to alpha m. The alphas are the outputs of the align function. The alphas are the weights we seek to find. This is just one feasible approach to computing alphas. There are many other alternative approaches. Don't be surprised if you find a different implementation of the align function. Here is another approach, and this is more popular today. The transformer model uses this approach. It has 3 steps. First, apply 2 parameter matrices Wk and Wq to Hi and S0 respectively. The 2 parameter matrices will be learned from data. The resulting Ki and Q0 are vectors. Second, compute the inner product of vectors Ki and Q0. Denote the product by alpha tilde I. It is a scalar. Finally, normalize the alpha tildes using the softmax function. Denote the outputs by alpha 1 to alpha m. They are the weights we need. Let's go back to the sequence-to-sequence model. We have found the weights alpha 1 to alpha m. Each alpha corresponds to an H vector. Next, compute the weighted average of the H vectors. The alphas are the weights. Let vector C0 be the weighted average of the H vectors. C0 is called context vector. The context vector C0 corresponds to the decoder state S0. Then we run the decoder network. It takes x'1 as input and then updates its state S. How to compute the new state? This is how the SimpleRNN updates its state. The SimpleRNN uses a new input x'1 and the old state S0 to compute the new state S1. Look at the figure. X'1 is the new input. In the machine translation application, it is the start sign. S0 is the old state of the decoder RN. The new state S1 depends on x'1 and S0. In the update of SimpleRNN, the decoder does not look at the encoder. The decoder's new state S1 is entirely determined by its previous state S0 and the new input x'1. If S0 forgot some information about the encoder's input sequence, then the translation will be wrong. A better strategy is to use the context vector C0 in addition to x'1 and S0. When we computed the context vector C0, we looked at all the states in the encoder. The context vector C0 remembers the information in the encoder. If we use C0 to compute the new state of the decoder, then the new state S1 will have full information of the encoder. S1 does not forget anything. This is one feasible way of updating the decoder state. The new state, S1, depends on the three vectors, x'1, S0, and C0. This method is known as attention. Its difference from the standard RN is the context vector C0. C0 is not used in the standard RN. Now we have the new state S1. It is a function of the context vector C0. C0 is the weighted average of the encoder states, so C0 knows everything in the encoder. In this way, the decoder's new state S1 knows everything in the encoder. Using attention, the RNN sequence-to-sequence model does not forget anything. Then we want to compute the next context vector. It corresponds to S1. To compute the context vector, we first compute the weights, alphas, using this equation. The ith weight, alpha I, depends on Hi and S1. The weight matters how well Hi and S1 are aligned. Look at the figure. The weights depend on the decoder's current state S1 and all the encoder states H1 to Hm. The outputs of the align function are alpha 1 to alpha m. Each alpha corresponds to an H vector. Note that we do not reuse the alphas computed in the previous round. Previously, when computing C0, we computed alphas. However, the new alphas are totally different values. Previously, the alphas are computed using S0. But here, the alphas are computed using S1. So the alphas here are different from the previous round. The previously computed alphas cannot be reused. We compute the new context vector C1 using this equation. C1 is a weighted average of H1 to Hm. The weights are the alphas. Look at the figure. C1 is based on alpha 1 to alpha m and H1 to Hm. The decoder takes x'2 as input. x'2 is the German word generated in the previous step. Then, the decoder Rn will update its state. The new state, S2, is computed using this equation. S2 is a function of the new input x'2, the old state S1, and the context vector C1. Now we have the new state S2. The next step is to compute the new context vector C2. Compare the decoder's current state S2 with all the encoder states H1 to Hm to see how well they are aligned. Alpha 1 to alpha m are the computed weights. We compute the new context vector C2 using this equation. C2 is a weighted average of H1 to Hm. The weights are alpha 1 to alpha m. Look at the figure. C2 depends on alpha 1 to alpha m and H1 to Hm. We are ready to update the decoder state. The decoder takes x'3 as input. x'3 is a German word generated in the previous step. We use x'3, S2, and C2 to compute the new state S3. Now we have the new state S3. The next step is to compute the new context vector C3. Compare the decoder's current state S3 with all the encoder states H1 to Hm to see how well they are aligned. Alpha 1 to alpha m are the computed weights. We compute the new context vector C3 using this equation. C3 is a weighted average of H1 to Hm. The weights are alpha 1 to alpha m. Look at the figure. C3 depends on the alphas and the H vectors. We are ready to update the decoder state. The decoder takes x'4 as input. We use x'4, S3, and C3 to compute the new state S4. Now we have the new state S4. The next step is to compute the new context vector C4. Compare the decoder's current state S4 with all the encoder states H1 to Hm to see how well they are aligned. Alpha 1 to alpha m are the computed weights. With the weights alpha 1 to alpha m at hand, we can take the weighted average of the encoder states H1 to Hm. Let the weighted average be the new context vector C4. Repeat this process to compute the new states and new context vectors. Once the generated token is the stop sign, we put an end to this process and return all the generated words. Each time we compute a context vector C, we need to compute the weights alpha 1 to alpha m. A question: what is the total number of alphas we have computed? To compute one vector Cj, we compute m weights, alpha 1 to alpha m. So each time we update the decoder state S, we compute m weights. Suppose the decoder runs t steps. Then we have computed mt weights in total. So the overall time complexity of attention is m times t. M is the encoder's number of states. T is the decoder's number of states. Here is a comparison. Without attention, the time complexity of RNN sequence-to-sequence has a time complexity of big O of m plus t. M and t are the lengths of the two sequences. This is a linear time complexity. With attention, the time complexity is big O of m times t. In machine translation applications, if a sentence is long, then attention is slow. While attention substantially improves the quality of machine translation, it makes machine translation much slower. To this end, we have learned how attention works. I'd like to use this example to show the meaning of the weights, alphas. This example is the translation of English to French. In the bottom is the encoder. Its input is an English sentence. On the top is the decoder. It generates a French sentence. Attention compares every decoder state with every encoder state. A line connecting an encoder state and a decoder state is a weight alpha. There is a line between every pair of encoder state and decoder state. A thick line indicates the two states are well aligned. That is, the weight alpha is big. The line connecting the two states is thick. It means the weight alpha is big, and the two states are highly relevant. This has an intuitive explanation. The English word area is zone in French. Each time when the decoder is about to generate a new state, it looks at all the states of the encoder. The weights alphas tell the decoder where to pay attention. This is why the model is called attention. When the decoder is about to generate the new state, the decoder pays attention to the encoder state at the position of the word area. Thus, the decoder is likely to generate the correct translation, zone. Let me summarize this lecture. In the standard sequence-to-sequence model, when generating the next state, the decoder looks at only its current state. The next state is based on only the current state. There is a problem with it. The decoder does not directly see the input sequence of the encoder. The decoder's knowledge of the encoder's input is entirely from the encoder's final state. If the encoder's final state forgets anything, then the translation will be wrong. Using attention, the decoder additionally looks at all the states of the encoder. The current state of the decoder is compared with all the states of the encoder. Using attention, the decoder has a better knowledge about the encoder's input sequence. Even if the decoder's previous state forgets something, the prediction can still be correct. Furthermore, the weights computed by attention allow the decoder to focus on a certain context. This is the reason why the model is called attention. The decoder not only knows everything about the input sequence, but also knows what is the most relevant and where to focus on. The downside of attention is higher time complexity. Let m be the source sequence length and t be the target sequence length. In the standard sequence-to-sequence model, the encoder goes one pass over the input sequence, then we will never look back at the encoder states again. The decoder generates the new states sequentially. The overall time complexity is merely m plus t. However, with attention, the time complexity becomes big O of m times t. The time complexity is much higher. It is because in every step, the decoder needs to look at all the states of the encoder. Attention is very helpful when the input sequence is long. It is because RNN models do not have long memory. However, when applied to long sequences, attention results in much higher time complexity. More computation is the price you pay for attention. Thank you for watching my lecture. The link to my slides are below the video. In the next lecture, you will learn self-attention. Self-attention is not limited to sequence-to-sequence models. Self-attention can be applied to all kinds of RNNs.